Now,
Man, some bodies up in here.
let's just start with basics. Let's just say that I had a rectangle in here. Okay?
Geometry.
Geometry. So, what's my vertical dimension going to be in? Pressure. Okay, right? So this dimension would be in pressure, which is going to be in newtons per
Meter squared.
meter squared. Then this dimension is going to be in,
Volume.
which is cubic meters. So when I find the dimensions and multiply newtons per square meter times cubic meters, I get
Meters.
newton meters, otherwise known as joules. So what do you think?
Wait. Why?
What do you think the area
Put it on me.
on a
I don't know why you
pressure
put it on
volume
me.
graph gets you?
Work.
Measured in joules.
Work.
Work. So here's rule number one. The area on a pressure volume graph gives you work. Okay? Measured in joules.
Me.
Joules or joules, whatever it is. Okay?
It's me.
All right. So we got that. So now I'm going to make this disappear. If I can.
Which one's the bigger me? Jules or me?
That is just kind of watch. Okay, all right. So, we're going to pick a point. I don't care. Let's call it 1.2. And now this is like 10 to the fifth because this is newtons per square meter.
Yeah.
Right? So these are big pressures, right? So this is like, here's atmospheric pressure 1.0. This is 1 atmosphere.
Yeah.
That's what we're under about right now. We got a volume of 0.01 cubic centimeters, which is about like yay. Okay. So here's what's important. I've got a coordinate pair, right? So this coordinate pair is 0.01 cubic meters and 1.2 times 10 to the fifth pascals, or newtons per square meter, whatever you want to call it. Okay? It's cool with that. So I've got a pressure and a volume, and let's say that the number of moles inside of here, to make it simple, are 0.1 moles. So I got 0.1 moles of gas inside this volume. I got this pressure, I got that volume, and I've got the number of moles. So what else can I find at that point? Temperature. So here's what's cool about this graph. As long as the number of moles stay the same, it's almost like a three-dimensional graph, okay? In the sense that you have pressure, volume, but here's what's important. At any given point, knowing the pressure and volume, it's exactly what Jason said. What else can you find? Temperature. So you only know pressure and volume, but you can very easily at any point find the temperature. Okay, so we're going to start with this. So I've got this pressure, 1.2 times 10 to the fifth. I've got this volume, and I've got this number of moles. So let's figure out what the temperature is going to be. So what are we going to do? Preston, what am I going to do?
You have to solve the temperature in NERD.
Perfect. So get your ideal gas law, right? So I've got
Oh, nutter.
PV equals nRT. So, Preston, how am I going to get the temperature by itself?
Divide by NR, they're the same.
Yeah, so I divide by NER.
NER.
Okay? So I've got my pressure, which is, and again, I just made up these numbers. I have no idea what this answer is going to be. So 1.2 times 10 to the fifth newtons per square meter times the volume of 0.01 cubic meters. And then N was 0.1 moles and 8.314. Even though your equation sheet has it as 8.31, ever since I've studied chemistry, this is 8.314, and that's what we're going to use. Just because we can. So, what do you get as the temperature?
1443.
1443. Pretty warm. Okay, especially because it's Kelvin. So that's going to be pretty warm. So out of this, I get 1443 Kelvin.
That's pretty hot.
That's not toasting. Yeah, we can make a lot of toast.
Yeah.
So even if you subtract like 273 from it, you know, to get it in Celsius, you're, you know, like 1200 and some change, so yeah, that's pretty warm.
Whoops.
We can certainly melt iron at this point, probably boil.
The
Okay.
70 Celsius.
So, we got the idea, it's hot.
Boiling. It's
Now,
like pumping iron.
At this point, here's what I want to look at. And I'm going to use my syringe, okay? And again, ladies, if you have a guy that says, oh, here, let me show you my syringe collection, run. So,
Relationship,
my dad's job.
relationship advice from Bird.
That's my dad's job.
No,
This
no.
answers to all the time.
so here's what I'm going to
Relationship
do,
advice with Bird.
okay? So, what I've got is a certain pressure and a certain volume and a certain temperature. So I'm going to model this with my syringe, okay?
Let me
So
show you
what
my
I want to
syringe.
do is I want to maintain the same pressure. And I want to take this line across to a bigger volume. So here's what I want. Physically, what has to happen to this plunger? If we're using this to model it, what are you going to do? You're going that.
Pressure's gonna. Is pressure
Yeah.
supposed to stay the same?
So, huh?
Pressure's supposed to stay
Pressure's
the
gonna
same.
stay the same.
Then temperature's gonna shoot up.
No, we'll get there. We're just talking about what's going to happen to the syringe, right? We'll get to temperature in just a second.
Okay.
So, I'm here, right? Certain volume. And then that volume is going to get bigger. Now, is work being done?
Yeah.
Yes. Work is being done. Why?
Because you're exerting a force over a distance.
Force is being exerted through a
Distance.
distance. Okay. Now, I'm going to go from 1.2, okay, and then I'm going to go over here to 0.03. So let me kind of do a little bit of eraser work here. Eraser work. So now, so somebody remember this number, 1443.
It's a pretty cool year.
Huh?
Pretty much when
Yeah, I don't know.
When did Christopher Columbus say?
1492. Not close. Or kind of close.
No, it wasn't actually fought in 1812. Okay, so here's what I'm going to do, is I'm going to take this line across like this.
Oh. Oh, there
Until I
you
hit this point.
go. Salvage
So
it.
at this point, I'm at 0.03 cubic meters, and my ball or pressure is still 1.2 times 10 to the fifth. So let's go to something that Lenny talked about. So as this line is going across, what am I holding constant?
Pressure.
Pressure. So this is going to be isobaric. Okay? Because I'm going to keep the pressure the same. We're going to increase the volume. Okay? All right, cool. Now,
That was him. That was me.
okay. So, here's what I want to look at. Let's go to what Lenny said. What has to happen to the temperature of the system?
It's gonna have to go up.
It's going to have to increase. Why?
Because you gotta keep the pressure. Things gotta make up for the loss in pressure.
Well,
Oh,
look.
yeah.
You got PV equals,
Everything stays the same,
And
so
RT,
you cancel
right?
out. It's just V over T.
do both sides have to remain constant?
Yep. Not
Right.
well.
So, as I go across, what's happening to my pressure?
nothing.
Nothing. It's isobaric. Pressure stays the same. What's happening to my volume?
It's increasing.
So I'm getting a bigger volume. Am I changing NER?
No.
Same number of moles, same gas constant. So if my volume gets bigger, the only way that can happen is what?
Two.
I got to increase the temperature. Okay? I've got to increase the temperature. So the only way that can happen, so physically, here's what I want you to look at. If I gave you this syringe, and I said, I want to make this happen. I want to make this go across, I want the volume to get bigger, but I want to maintain the same pressure, but I'm going to make the temperature go up. So what would you physically do to the syringe?
I would plug it and breathe real hard on it.
Not quite.
No.
Wouldn't it work?
They wouldn't heat it up enough. You'd put it over a fire.
But you want to heat it up. That's the main point, right? So you want to increase the temperature. Now this is why it's handy to think of this in terms of second graders named Timmy.
Yeah.
So what am I doing to the size of the second grade classroom?
Increasing it.
I'm making it bigger. Now, remember, how pressure sensors work is that you have little particles, nitrogen, oxygen, and those type of things, that are bouncing off the pressure sensors, just like little Timmies are bouncing off the walls. So, here's the deal. I'm making the temperature go up. So what's happening to the kinetic energy of Timmy? It's going up. We've given Timmy a bag full of Skittles. Okay?
We give
Timmy
every
loves
Timmy a
Skittles.
bag.
Okay? So he's like going, ah! Okay?
Like a
But,
dinosaur.
but, so if we kept the size of the room the same,
Hit the wall more times.
and we increase the temperature, what would happen to the pressure?
Increase.
Because not only are you going to have more collisions, but the collisions are going to be having more kinetic energy. Yeah, Timmy's like, oh, okay?
Oh my god.
Yeah,
Timmy's
well,
giving himself milk
Okay.
dogs.
Oh,
No.
CTE. Timmy's giving himself CTE. Just, God,
made a mistake.
You dropped Timmy.
I did. Actually, I found Timmy. Big difference. So,
Threw Timmy against a wall.
The
so,
wall.
so here's the trade-off. We're going to have more energetic collisions with Timmy when he hits the wall, but because we're making the room bigger, what's going to happen to the number of collisions? It's going to lower it. So that's going to be our trade-off. So we're going to maintain the same pressure. Timmy's going to be hitting the wall harder.
I just imagine this kid running full speed at a wall.
See, I would write this book and animate it, but I would probably get in so much trouble.
Yeah.
Because I have this vision of like, you know, like the, oh, what's the
his vision.
movie? The Incredibles?
Oh yeah, Dad.
Yes.
Damn! Okay? So you can animate this whole thing, okay? Anyway, they probably go, oh, this is abuse, you're running Timmy into the wall. It's a figure of speech. Timmy bounces back, he's fine.
Timmy's took an L last night.
It's okay.
But
There's no lasting brain damage. It's okay. Or game damage,
last night
whatever.
took an L.
Okay,
His health got
so
bounced back.
here's the
You know
question.
that's what you do when I get bounced back.
He never ate Skittles again.
Last night took an L.
Okay. So,
You have to get
could
the
I
sales
calculate
permission.
this temperature?
So we
Yeah,
got
if
bounced
you want.
back.
I
If you're
could.
real,
I bet.
you know how
Okay.
to bounce back in your body.
So,
You don't know
is
what
that
body always
temperature
on
going
a
to be
fucking
bigger or
job,
smaller than
but-
1443?
Bigger.
Bigger. So, I got, so somebody run the numbers, we're going to do the same thing, take the pressure of 1.2 times 10 to the 5th, times the volume of 0.03, divide that by the same number of moles of 0.1, and R 8.314.
It's just triple, right?
Yeah,
I don't know.
yeah. Oh wait, this is
So what's the new temperature?
tricky. 4330.
4330.
Yeah, it's just triple.
Yeah, it's just triple. Oh, how cool is that, right? Well, how cool is this?
I wasn't confident in my answer, Jason.
So we've just tripled the amount of kinetic energy. So here's what's going to happen. Here's what's going to be important. Energy has to flow into the system. Now, on the back side of this, and I will give you these equations, okay? So on the back side of here, there's some very, where's it at? Oh, there it is. So you got delta U equals Q plus W, that's one. Work equals negative P delta V. And the other one is that delta U equals 3/2 NR delta T. Now, let's talk about what delta U is. So, delta U is this weird kind of concept in the sense that it's the sum of all the types of energies that are in a system, okay? So it could be the kinetic energy of the particles, it could be the rotational kinetic energy, so if Timmy is doing like cartwheels as he goes, okay, instead of just running, so he would have rotational and kinetic energy.
Bouncing the
So,
walls
delta
with
U
cartwheels.
is very, very hard to directly measure, mainly because of the fact that if you go to a science catalog and go, hey, I need to buy a delta U probe. You're not going to, okay? You cannot measure directly delta U. Now, this Q is the same Q that we've been talking about in terms of energy flowing in and energy flowing out. W is going to be work. So there's two things about delta U. It equals 3/2 in our delta T. Here's this gas law constant, okay? And this is why this is going to be important. Because notice over here, this is nert, right? So if you remember from your perv nert equation, what do you get when you multiply the nert side? What units do you get?
Joules.
You get joules. What'd you say?
It's a perv.
You get joules. So what do you think delta U is measured in?
Joules.
Now, work equals negative P delta V, and I'll explain the significance of this negative sign in just a second, okay? And then you got delta U equals Q plus W. So here's what I want to look at, okay? Here's what I want to look at. In this situation, was there a change in temperature?
Yep.
Yeah.
Yes, there was. There was a change in temperature, right? Because we went from 1443 up to 4330. We tripled the temperature. So there was a change in temperature. So right away, I know that because I've got, and what's going to be the sign of that change in temperature, positive or negative?
Positive for that
Positive.
situation.
My temperature final is going to be greater than my temperature initial. So this is going to be some positive number. I got N and R. So if your delta T is positive, what has to happen to the sign of delta U?
Positive.
It has to be positive. Oh, okay. So what that means is that the overall energy in the system is increasing, okay? My overall delta U is going to be a positive number in this case. So if I come back over here, okay, going across like this, I'm going to have a positive delta U, okay? So I'm going to start with this. This is going to be important. I'm going to have a positive delta U because I have a positive change in temperature. Okay, so that's one way we can calculate that amount. We'll get back to it. Now, let's talk about this. Imagine that I draw these lines down like this. Looks surprisingly like a
Rectangle. What?
What? Is work being done?
Yes.
Work's being done. How do you know?
Because it's a rectangle.
It's a rectangle. And we said the area is going to represent
Work.
work. So if there's area underneath here, guess what?
It's work.
Work's being done. Now, here's what we're going to look at. Is that work equals negative P delta V. So in this situation, basically, these are just the dimensions of the rectangle. Okay? You've got your pressure, right? And then you got your change in volume. So it's just the dimensions of the rectangle. So in this case, I'm going to have negative pressure, which is what, 1.2 times 10 to the 5th liters per square meter. Now, this is going to be V minus V naught. That's muy importante. This is V minus V naught. So what's my final volume?
0.03 or whatever.
Final volume was like, what, 0.03?
Yeah.
0.03.
Okay, so
And then
that's going to be
0.01.
0.03 cubic meters minus 0.01 cubic meters. So, if I do the math, here's what's going to be important. As the volume gets bigger, what's the sign of delta V?
Positive.
So that means my work, though, is going to have a negative sign. So this is going to be huge. The work's going to be a negative sign. So, anytime you make something bigger, work's going to be a negative number. So, somebody run the numbers. Well, that's going to be 0.02.
It's
so
negative
that's going to be
2400.
negative 2.4. No.
Yeah.
Yeah.
Times 10 to the third.
Yeah.
Which is just 25.
Yeah, which is just 2,400. Now, here's what's important. I can make this analogy in the sense that at some point, I'm gonna have to write a will, God forbid, and I'm gonna have to decide, hey, what do I do with
You haven't done that
meager
yet?
earnings that I have?
I'm doing that when I turn
So-
21.
I'm gonna go to Lenny, okay, because I've taught Lenny, I love Lenny, okay?
Oh.
I get everything.
You get Hank.
Yeah, do I get Hank?
You get Hank.
Who
Yeah.
gets your gallbladder?
That's long gone. Okay, so, here's the deal.
Stop.
Whatever money I give Lenny, okay?
All of
Here's the
it.
condition though. Lenny has to build something. He has to make the volume of something bigger.
I'll build
Okay.
a little Tinker Dog house. I'll build a Tinker Toy house.
So you don't get to keep the money. You have to do something good with money. I don't care what you do with
Oh,
it.
dang.
Okay? So I'm gonna leave you $5,000
Ooh.
and I'm gonna say, but you don't get to keep it. But you get to choose what you do with it. Okay? So I'm gonna leave you $5,000. I'm gonna say, you have to build something. You have to make the world a better place. So even though he's gonna be given $5,000, he's gotta take $5,000 and go build something. So whenever volume gets bigger, work's gonna be a negative number because it's costing energy, because you're making something get bigger.
Build a statue of him.
So when something expands, it costs energy. So here's the simplest way to
You're getting the
experience it.
statue.
Put your hands in front of your mouth, okay? Have your mouth wide open, okay? And blow on your hand. How does it feel?
No different.
Feels hot, right? Feels hot. Now I want you to do the same thing, but then I want you to like pucker your lips.
No, you're actually gonna tell us why this works now?
Yes.
This is like a big meme. Like, why does this actually work?
And then blow on it. How does it feel?
No different. It's
Feels cool, right?
Yeah.
Now, what's the air doing once it passes through your lips?
It's expanded.
It expanding. And that costs it energy. Okay? So it feels cooler because once it passes across your lips, it pushes against the atmosphere that's trying to keep it down, and it loses energy. Are we good, Lenny?
Whoa! No.
Whoa!
That's crazy.
I didn't never know there was an explanation for that.
That was just a Mr.
It doesn't
Biology.
work, it's just like a big chunk of air. Or like
Yeah,
a
because
wet-
it's not
a big old mouth. Wait, you just need to get a big old mouth, and that way you can
You're
feel hot
not
air.
doing work on it because you're not compressing it. But then, once you compress it and then it
I'm gonna
expands,
show them the meme.
it cools because it has to expand.
Oh.
Wait,
Makes
is that
sense.
is that like airplane engines?
Bro.
Where they have to compress the air?
Yes.
Bro.
What if you breathed out and it became a solid in your lungs?
Well, I forgot about the solid
The
lung.
solid in your lungs, yeah.
Jacob's look down.
down.
It's down and shaking.
He's sleeping.
Go!
So there's one day where I really want to wet my hand with your sink and just give them all.
I don't know.
I did it one day when you weren't looking, but it's alright. I wouldn't do it again. But it was funny.
It really is just
out.
Okay.
I really
All right.
can't make fun of him because I
Now,
definitely already slept.
Here's what I want to do. I actually want to count, now that I've got my W, okay, this is negative, right? So this means that it's costing us energy. So here's one of the most important things you have to realize when you do thermodynamics is that it's prepositions. So what's happening is that the gas is doing work on the surroundings. So this is about preposition. So the code for saying, oh, the work does, or the system does work on the surroundings is because that is making the volume bigger. So if you look at what happened when I had the plunger, and I had that thing and it had it compressed, right? It didn't like that. So when that gas pushed that up, what happened to the volume? The volume got bigger. So that means my work was going to be a
Negative.
negative value, so it was cooling the gas down. So it was costing energy because it had to push against the cylinder that was trying to keep it down. Okay, it was raging against the man, right? Oh, you
Raging
can't
against
hold
the
that.
machine. Let's go.
Okay, now, here's what I want to do.
State.
I actually want to calculate delta U, okay? We've had that capacity. So I got 3 halves moles was 0.1. We got R, which is 8.314 joules per mole Kelvin. And our temperature change, what were the two temperatures? What was the higher temperature?
4330.
No, what was the higher temperature? 40 what?
4330.
Yeah,
4330
4330 and 1443.
and 1443. So somebody subtract those numbers out.
I'm still shook.
Okay, now
I'm sorry. I'm still shook.
Two what?
2887.
I didn't expect that to be this way.
Okay, Kelvin. Now again, this is change in temperature, so it doesn't make any difference whether it's Celsius, Kelvin, doesn't make any difference because it's just a change in temperature. So, what do you get
For the total or
for the delta U?
3600.
3600?
Pretty even, actually.
Okay. Now, here's what I want to look at. This is my 3600 joules. What was our work? What was my work number?
Negative 24.
Negative what?
24.
Negative 24?
yeah,
2400.
2400.
Oh, 2400. Now, so can I figure out what my value of Q is?
probably, yeah.
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 Yes.
Yeah, doing what?
6,000.
Adding it.
Yeah, add that over, I get 6,000.
But some people can't add things.
So, what did you say?
Some people can't add Chase.
Okay, now, here's the big picture. Okay, here's the big picture. So here's what's happening, is that I have, in a situation upon my passing, I'm going to leave Lenny 6,000 joules of mine.
6,000 joules?
6,000
joules.
Okay? Right? Stop. Okay? Stop.
He's gonna take your. He's gonna take your.
Didn't take away, Jules.
Dr. Potts is walking on. It's like, today's high
He's
school
18.
teacher fired.
Hey, I'm 18 though.
I don't care.
I'm 18 though.
So, here's what's going to happen. I'm going to leave Lenny $6,000. But the condition is, he's got to spend $2,400 of it to make the world a better place. So how much does he end up with? 3,600. Okay? So, this is the amount of thermal energy I would have to dump into the system. Of this 6,000, 2,400 of it is going to make the volume bigger. This is what I have left over. Now, contemplate this. What if I lock this thing in place and I don't let it expand? I give Lenny $6,000. What's the delta U going to be?
6,000.
6,000. Because he's not doing any of it to make the world a better place. He's keeping all of it. So what do you think is going to happen
Show
to
me
the
the
pressure?
money.
Then if I lock this thing in place?
It's gonna shoot on it.
Why?
Because it's got nowhere to go.
Yeah, what's all of that, instead of that energy, some of that energy going to expand it, all of that energy is going to stay within Timmy's. Timmy's not going to make the room a bigger place, right? So this is like, rah! Pressure's going to go sky high.
Oh,
Okay.
that sounds like a cat.
This is the mental
Yeah,
that's a
picture of
good
your
So-
Don't
nose.
be a Timmy. Do good in the world.
This is true.
That's gonna be my.
Or don't be Lenny.
Yeah. It's gonna be my I'm number cell one. phone.
Yeah.
It's gonna be my.
Okay.
Number one.
So, here's what
be
I
my
want you to
text.
look at. So in this situation, I've got a positive Q. Oh, hold on, here's my graph. There it is. So as I go across, I've got a positive delta U, because the temperature's going up. I've got a positive Q, because of the fact that I'm dumping energy into the system. But what about my sign of work?
Negative.
That's going to be negative work, okay? So now, if I reverse this process and bring it across, what's going to happen? If I start here, so if I take that syringe, okay, and I've got a lot of volume, and I'm going to make it go down, I'm going to have, if I reverse it, what's going to happen to the sign of delta U? It's going to be
Negative.
So what's going to happen to the temperature? It's going to decrease. What direction is the thermal energy going to flow? In or out? Thermal energy's got to flow out, because now we've got to have a negative delta U, or delta Q, okay? Q has to be a negative number. Volume becomes smaller, work becomes positive. So if I reverse this, I change the sign on all of it. So what I would have to do here is I would have to take this and drop it into like an ice bath, where energy could flow out and the volume would get smaller. Now, this is the most complicated one. This is why I did this first, okay? This is the most complicated one. So, we've calculated everything, delta U, Q, W. It's the only one we're going to have to worry about all of these, okay? Now, I'm going to start over. Same situation. That was 1.2 times 10 to the 5th, and that was 0.01 cubic meters, and then I'm going to end up over here at 0.03. Now, I'm going to end up at 0.03 cubic meters, but now I'm going to come down like this. Okay? So now I'm going to have a curved line. So this is what we call isothermal. So what's going to happen on an isothermal expansion? What's going to stay the same?
Temperature.
Oh.
So just pressure and volume, isn't it? Yeah.
So now, if you look at an isothermal, this is why this is simple. On an isothermal, what's staying the same?
Everything on that right side.
Right.
Temperature staying the same. So the inert's staying the same, right? So what's happening to my volume?
Increasing.
It's getting bigger. So my volume's getting bigger, so what has to happen to my pressure if this side stays the same?
Smaller.
Oh, it's going to drop. So I'm going to get a bigger volume, so I've got to drop the pressure.
P1, V1 equals P2.
Okay? To get the same energy. True? Volume's getting bigger, I've got to drop the pressure. So what's happening on my syringe is this. I'm here, I'm going to make the volume bigger. Volume's going to get bigger. But what's going to happen to the pressure inside? Pressure's going to get smaller. So now, this is isothermal. So are the Timmies hitting the wall with the same amount of kinetic energy?
Yes.
Yeah,
Yes. Why?
because they're the same temperature.
Didn't change temperature. So they're hitting with the same amount of kinetic energy.
They're just not doing it that much.
Yeah.
They're not doing that much. Why?
Because there's a
They're
bigger.
further.
There's bigger room. Okay? We made the room bigger. So we didn't change the kinetic energy of the collisions, but we made the collisions less frequently because we made the room bigger. Now, here's what's important. This is isothermal. What's my value of delta T?
0.
It's a big fat goose egg, right? Not changing temperature. That's by definition, this is what isothermal means. No change in temperature. So, knowing this, we said that delta U equals 3/2 NR delta T. What's my change in temperature?
0.
Nothing.
It's a goose egg. What's my delta U?
Nothing.
Goose egg. So guess what? Delta U equals 0. So if delta U equals 0, what else does delta U also equal?
Q plus W.